Let's talk about alternating series. On the screen, you can see here a summary of the alternating series test. So we have a series that starts off with some formula AN, but we're going to split it, if it's not split already, into its plus minus part and its magnitude part. So all the BNs should be positive. This is just the actual formula. And then you have either -1 to the n or n plus 1 and -1, whatever, that creates the plus minus for the terms. All right, so an alternating series, because you're adding and subtracting as you go, it's actually very easy for these to be convergent. You just need to meet these two conditions here. So you need bn plus 1 to be less than or equal to bn, meaning the magnitude of each term is less than or equal to the one that came before it, at least eventually. And then we also need the limit of those magnitude terms to be 0. As long as those two conditions are met, you conclude that your alternating series is convergent. All right, so if we're asked converge or diverge questions for a series that has a product negative limit, our minds should automatically go to the alternating series test. So you can see on the screen now, this is the example I'm going to talk about in this video. So I have the sum from n equals 1 to infinity of -1 to the n over n to the n. So the question is this series conditionally convergent, absolutely convergent, or divergent? Those are the three options for an alternating series. And if it's convergent, find the partial sum that estimates this entire total within 0.0001. All right, so let's tackle converge versus diverge first. Okay, this is an alternating series. So I'm going to do the alternating series test. I do want to realize that the -1 to the n is kind of the on-off switch for the plus minus sign. So the bn, the magnitude part, is 1 over n times 2 to the n. So when I'm showing like decreasing terms and limit, it's the 1 over n to the n that plays the role of these, just the magnitude part of these terms. Okay, so we want to check that the terms are all less than or equal to the one before. So I'm going to write the n plus 1 term. So that's 1 over n plus 1 to the n plus 1. And I'm going to compare it with the n term, 1 over n to the n. This one clearly has the bigger denominator with the n plus 1 term. Bigger denominator is a smaller fraction, so the inequality goes this way. And I've met the first condition for the alternating series test. This one happened to work out. Remember, if these formulas are extra complicated and it's not particularly clear to you here which one is less, what you would do is switch into the continuous function version of your formula and investigate the derivative of that function. And you're aiming to show that its derivative is negative, which would also show the decrease. But not needed here, so we'll move on to part 2. We also want to show that the limit of the bn terms, that's 1 over n to the n. We want to compute this limit. We have 1 over something getting absolutely humongous toward infinity. So this limit is 0, which is what we needed for the other part of the alternating series test. All right, so convergent by the alternating series test. And that actually only narrows down our answer a little bit. We can at least exclude divergent, but this hasn't answered whether it's conditionally or absolutely convergent. That's going to be a separate test. So to investigate conditional versus absolute, we want to consider the absolute value version of this series. If this absolute value version also is convergent, we'll say absolutely convergent. If this version is actually divergent because it lost the plus minus thing and became divergent, then we would say this is conditionally convergent. Notice that in this formula, the absolute values effectively just take out the -1 to the n because it would make every term positive. So really we're looking at the series 1 over n to the n. So just converge or diverge for this new series. Notice that we can't use the alternating series test, right? Because this isn't alternating. So what we just did no longer applies. There's a couple different ways to figure out if this one's convergent or divergent. I'm going to use the direct comparison test with 1/2 to the n. If I exclude this n right here, I get 1/2 to the n, and if I write it as 1/2 to the n, I recognize it as a convergent geometric series. So I'm going to note to myself, what I'm comparing it to is convergent. If it's the direct comparison test, I am hoping that I can show my terms are less than these terms. So my terms are 1/n to the n. And in fact, these really are less than 1/2 to the n, which is the same as 1/2 to the n. Bigger denominator is the smaller fraction. So this is my smaller fraction. All right, so my terms are less than the terms of a convergent series. So this is convergent, which means the series from the beginning here is absolutely convergent. So I'm going to choose absolutely convergent. And now I can move on and answer the end of the question. So if it's convergent, which it is, find the partial sum that estimates this entire sum series within 0.0001. So I'm going to mark a change in task here. We want the error total sum minus partial sum to be less than 0.0001. Now we have a theorem that says if your series is convergent by the alternating series test, only for the alternating series test, then this difference, we know, is always less than or equal to the next term in magnitude. So here we can drop the -1 to the n part and just use our Vn, which is 1/n to the n. So essentially, we just need to find which term in this series has magnitude smaller than this, and then we can conclude what we want to do. So we want to find n such that Vn, I'm not going to bother with the n+1 here. I'm just going to find the number that has this property, and then I can backtrack it to the statement I need here. So I want Vn, which is 1/n to the n. I want to know when that is less than 0.0001. There's two ways to get to the answer here, which is n equals 10. One way is you could just kind of start plugging in values of n. So 1/3 to the 3, 1/4 to the 4, and keep going to get a number in your calculator that's less than this. Or you could do a little bit of algebra. This one's tough to solve all the way, but you could divide over the 0.00 here, and then bring the n to the n here, and you would get 1/0.0001, which is 10,000. Less than. We want 10,000 to be less than n to the n. This kind of algebra, though, is tough to complete. So from here, you would still be plugging in numbers experimentally, trying to find what number actually makes this happen, remembering that n can only be integers. Okay, so I'm going to pull out my calculator here, which we don't often do in this class, but right now we need to. And I'll try 1/, let's say, 5 times 2 to the 5th. 0.006. All right, so I need it even smaller than that. So I'm going to go up and we'll try maybe to the 9th. 1 divided by 9 times 2 to the 9th. That's 0.0002. So we're really close. If we do one more, if we do 1/10 to the 10. And we finally get a number that's smaller than 0.0001. So 10 is the first integer value for which this is less than. Okay, look at the calculator right here. Okay, so that means that we need V10 to be this guy here. So if this is B10, that means that we need S9, which is the ninth partial sum. So our answer here is find the partial sum and estimate the sum. So we're gonna say use S9, which is the sum of the first 9 terms of this series here. If they asked us to actually estimate within that, we would have to sit here with our calculator and add up the first 9 terms of this series. But as it is, we can just answer use the ninth partial sum, and that'll have the accuracy that we want.